believe if you are experienced user of rheometers, you always have a very specific geometry size, like 8 mm, 20 mm, 60 mm. So you have a very fixed area at the top plate. So when you set an experiment, they're going to move to displace your sample at particular preset displacement depending on the strain percentage or the shear rate that you need. Of course, this displacement is being governed by time, so you need to set the speed, such as you need to set this shear rate, how fast they will move, as well as how far you want them to move. So typically, shear stress is generally a force over area, which is the geometries that you use according to size, as well as a shear strain, which is a displacement x as a function of time over Ty, which is the sample thickness, which is also the sample gap. The sample gap is very important for you to fulfill with all your sample. And finally, you have a shear rate, which is simply using the shear strain over the time. So you have a gamma dot. So sigma, gamma, and gamma dot is a basic parameter symbol that you need to understand. And as of course, you have the viscosity as well, which is a noun, which is governed by the shear stress over shear rate. Well, let's look into rheometers. So a rotational rheometers is not going to move your sample in a linear manner, but they are going to move in a torsional manner, which is in a rotational format. So now the calculation will be slightly different, okay, in relative to the simple linear flow. Now you are going to move in an angular motion. So you have an angle. So you need to recognize some symbol as well, the omega symbol is sample thickness as well, the sample height, and the geometries, radius, as well as the theta, the angular motor displacement, or in short, angular displacement. Okay, so this is what we are going to use all these parameters to calculate your shear stress, shear strain, as well as strain rate or shear rate. Yeah, the same. So typically, the shear stress that being calculated by a rotational rheometers will be 2 over pi r cubed times m. So m is your torque. So this torque is always a range in your instrument specifications. So in any measurements, the torque value will always need to work within that range. Okay. While for strain is equals to the radius of the upper plate over the sample height times the angular motor deflections. So typically it's a displacement that you move in an angular format. So it's going to be in radian format. Okay. While the strain rate will be always R over H times the angular velocity. So typically it's radian per second. So these three items here, torque range, angular displacement range, and also angular velocity range will be always specified in the rheometer's specifications. And these are the basic parameters and units that always need to remember: shear stress, shear strain, strain rate or shear rate, modulus, shear modulus. We are always going to use the shear in front of all of these terms because you are going to shear your sample with rheometers. Last but not least, in a transient test, you always have a compliance as well. And finally, you can get the viscosities via rotational tests. And these are whole lots of symbols that what does it stand for when you're trying to read a rheometer paper or results, that you need to familiarize with all these symbol and what does it mean. Okay. So now let's dive into rheometers by T Instruments. So T Instruments is selling rotational rheometers. So we have in general two technologies. One is the SMT technology, separate motor transducers, and the other one is the CMT, which is the most common one, HR, the discovery hybrid rheometers, where we have combined motor and transducers. Separate, you have roll head, so lower and upper. For combine, the transducers and also the motor will be in a single positions. Okay. Motor is used to apply force to move the sample, while transducers is to read the sample displacement caused by the motor. So just for information on that. So in general, what does a rheometer do? So typically, they're going to measure and tell you about the sample viscosity as well as sample viscoelasticity's properties. So what kind of sample that they can handle by a rheometers? Basically, they can handle sample in different physical state, include fluids, semi-solids, as well as solids. But you need to have a correct accessories to target each of these materials in different physical states. Okay. So a rheometers is very simple. Okay, to be honest, you just have to set up command how much stress required to apply to a sample, and you will try to achieve certain strain that required by you. So to run the rheometers is very simple. What is most challenging is to interpret the data. So from a rheological deformations, typically is to study the sample flow behavior and deformation of a matter. Flow behavior typically on viscosity measurements, while deformation of matters typically relate to viscoelastic properties. Later in this presentation, I will share more about in details for these two common tests. But before that, we need to understand how does this shear stress or shear rate or strain rate being measured from the rheometer's specifications. So in any rheometer specification, you always have these three main and key specification that you need to understand. First of all, is torque. Torque is actually force applied in a rotational manner. That's why we name it as torque, which is in Newton meters. While angular displacements is how far rheometers can displace a sample, and angular velocity typically related to the speed of deformations. So these are the three key parameters that will determine the quality and your rheometer's performance. And how does we actually get these sample parameters that we need to calculate the viscosity and modulus? So each and every geometries or accessories that we provide will always have a fixed stress and strain constant. So these two constants is generally governed by the sample plate, parallel plate, or Conan plate for cup dimension itself. So this kind of constant you cannot change. Okay, it's gray out. If you are using our DHR right now, you can check the stress and strain constant in the meter tab. It's always gray out. Nobody can touch this. That's why it's very important to have a smart swap, because it will recognize that geometry is to have a very specific and unique constant to convert all these raw signals into sample parameters. So this is the equation for modulus. This is what you can see in the spec, and this is what you need to describe the geometries correctly. For viscosity, similarly, you need to also make use of the torque and angular velocity multiplied with the geometric constant, which is your stress and strain constant, in order for you to get the shear stress as well as the strain rate for you to calculate the viscosity. So beside these three typical important rheometer specification, we also need to consider the frequency range that you can go in hertz. Okay, beside the radians per seconds, you also need to have a normal force sensor. So what is this normal force sensor for? Well, imagine if you have a thermoset. So thermoset, typically when you heat up, they're going to cure. When they cure, they're going to start to shrink. So when they shrink, the normal force will typically go to below 0. If it's go to below 0, means your sample is not touching the sample. Okay, that's why you always have a normal force or axial force regulator in the software to make sure that always maintain at 0 plus minus 0.1 newtons to ensure good contact, especially for samples that involve huge physical changes like thermoset from liquid to shrink solid.
Mr. Josh,
Yeah,
regarding the liquid sample, right?
yes.
What is the specification or dimension for liquid? Maybe there are certain range that you can share.
What do you mean by range?
Range of
And
liquid, range
all
of
type of
sample. There are
typically
some limit.
rheometers
Is there?
can
I mean, is there any limitation for the liquid?
liquid doesn't have any limitations, but
All liquids is
okay,
capable to be tested, right?
yes, it can be tested. It can be tested.
Okay.
Okay, that's why you have multiple accessories that can be compatible to the DHR or HR parameters, like
Yes.
these cylinders. If let's say you have a very watery sample that cannot stand on this flat surface like water, ethanol, IPA, orange juices, okay, you need to use a cylinder to contain it, okay. But for cone and plate and parallel plate, typically is for medium viscosity sample. I'm talking about medium means 1000 centipoise and above. Okay, like honey that can stay on this flat surface. Then you may go for cone and plate and parallel plate. Of course, parallel plate and cone and plate, they have different sizes as well that I will explain to you later. Which one to go for? Okay, if let's say you have solid sample, so you have a very specific shape, like solid, then you need to go for different geometries, which is torsion rectangulars or DMA, film tensions or compressions, clamp. Okay, so rheometers can handle samples from a very low viscosities all the way up to solid samples with different geometries options that you can have to add on layers, or you can get it at the very initial stage. Yeah. So how do we actually choosing geometry size? Well, you need to assess the viscosity of a sample very generally. So if let's say you have a milk sample, okay, quite low in viscosities, okay, you can go for larger surface area, which is 60 mm. So larger surface areas will indicate will increase the sensitivities of the rheometers to be able to measure a very low viscosity sample. But for medium viscosity like honey, you can go for 40 mm. Well, if it get thicker like caramel, very thick, almost have structures, then you can go for 20 to 25 mm or even 8 mm if you feel you cannot generate a good shear stress on your samples. Well, typically, of course, these are the geometry size available for selection options for any type of samples that you want to assess. So beside parallel plates for samples that which is very slippery, so you can go for sandblasted or crosshatch, typically to hold the samples in place. And when you have a sandblasted and crosshatch surface, typically this is for tests like you want to just to get the sample transition temperatures like TG, then it's okay. Okay. For sample that will evaporate, you can go for geometries that can equip with the solvent trap, or you can just go for a normal without the solvent trap. For temperature RAM test, you can go for geometries come with a heat break as well. For constant cylinder, we have multiple selections of the vane rotor, helical rotor, starch pasting roto, cup and bob roto, single wall, and also double wall. So double wall typically is for extremely low viscosity samples, like sample which is below 1 centipoise, like water. Okay, and this is for sample can be like oil, Newtonian oil. Then you can go for cup and bob. For gelling materials like starch, starch is a very special materials when gelling. That's why you cannot use typical cone plate to do starch. So you need to have a starch pasting. For example, like suspension, that you have a visible particles within your solutions, then you can go for helical or vane roto for this accessories. But for parallel plate, you remember you have a strain and stress constant, okay, in place. So this is how we calculate the stress and strain constant. So typically, you need to have a radius and also the sample height. So for parallel plate, remember, you need to specify your sample height. So it can be ranged from 2 mm all the way down to 0.5 mm. But by default, it's always 1 mm or equivalent to 1000 micron. So when to use parallel plate? So typically, parallel plate is for sample, liquid sample, but it's slightly thicker liquid that can stay in place on a flat surface. Typically for soft solid, like gel materials, cream materials, crude oil materials, okay, and as well as epoxy like thermostatic materials or sample with large particles. So you can use this. With sample slightly with longer relaxation time, which is more structured samples or structured semi-solid. For temperature ramp and temperature strip, it is compulsory to use parallel plates. You cannot use cone plate to measure temperature ramp or strip measurements. And also for material that will slip, you need to have a parallel plate that can attach a cross hatch as well as sandblasted plates. And it's only require very small volume of samples, typically 0.7 ml, mostly it's 1 ml, depending on the plate size that you have. So rule of thumb, when these surface areas of the plate size decreases from 60 to 20, the shear stress will eventually increases due to the stress constant. The radius decreases, the stress constant in general will be increases. But for plate gaps, the smaller gap that you go, it will increase the shear rate, okay, with a similar angular velocities that you can have in your Rheometers. So just for information, for parallel plates, they are going to have effective shear rate gradient. So in the middle here, you have sample which is static, not moving. So when you set, let's say, at a strain like 2%, okay, or shear rate 2 or 3, only the outer layer here will follow what you set at maximum, okay, and the shear rate will decrease when you go to the edge. You'll get slower and slower, slower and slower. So you're going to have a shear rate gradient here. So when you're using a parallel plate, it is important for you to trim the sample, but not over trim, because the majority of sample thickness are going to be coming from this edge. Okay. But for cone and plate, typically when you want to do a viscosity measurement, which is a rotational test, then I always advise customers to go for cone and plate because it always have a constant shear rate across the sample. Okay. So when you have this strain constant and stress constant, typically a truncated cone and plate, you're going to have a cone here. Why truncated? because you have a cut. Okay, it's not going to be like a cone, like a very tajam cone here. You have a truncation gap here. Okay, it's a cut, which is very specific. And the strain constant is always governed by 1 over beta. So beta is actually the angles, the truncated gap angle here. While the stress constant is governed by 3 over 2 pi radius cube. Okay. So when to use a cone and plate? Cone and plate typically for material that will flow. Okay, flow means typically you have not very solid materials that I'm talking about, typically for oil. Okay, if let's say you want to measure oil materials or surfactants, then you can use a cone and plate. Typically, if you want to go for very high shear rate, which is above 1000, so a cone and plate is your choice. Okay, because the gap is very small, even smaller than the parallel plate. Just like I mentioned, right? If let's say you have a smaller gap, the shear rate maximum can go could be higher. Okay, typically for unfilled polymers, but it can only go for isothermal test, means single temperatures test in a single measurements. Typically require very small volume due to the gap is even smaller as compared to the parallel plate measurements. Just for information, parallel plate, you can adjust the sample gap to accommodate for particle size that you have. But in cone and plate, you cannot adjust the sample gap. It's always fixed according to the recommended truncated gap there. So similar, shear stress will increase when you decrease the surface area of the cone diameters, which is from 60 to 20. Similar thought applied to these two geometries. Of course, the shear stress generated will be higher for 20 mm as compared to 60 mm. While the shear rate will increase as well when the truncated gap getting smaller and smaller, which is governed by this truncated angle or cone angle. But there's a limitation on the cone and plate due to you cannot simply adjust the gap like parallel plate. Typical truncation height for 1 degree, 2 degree, and 4 degree will be as stipulated here. Let's say today I'm using 1 degrees, typically 30 micron, let's say. So my largest particle size in my sample when I intend to use this 30 micron can be only 3 micron. Okay, because the gap must be 10 times larger than the largest particles in your sample. So for sample loading part, regardless today you are using cone and plate or parallel plate, please do not over trim a sample up to this stage. Okay, because the majority of a sample thickness is coming from these parts. Okay, overfill is better than underfill, but still you may get, if let's say you have a very sticky sample, so you may have a drag along the edge, could induce slight increase on your viscosity measurements or modulus measurements. So typically you need to have a correct filling. So cone and plate, parallel plate done. So we have also the concentric cylinder. So when to use concentric cylinder beside, let's say, if your sample cannot stand on the parallel plate? It's very good for those highly evaporated sample because the sample size for concentric cylinder is way higher than the cone and plate. So it will eventually reduce the sample losses when you place your sample inside a cup instead of flat surface. And of course, their strain and stretch constant will be slightly more complicated, but typically it will be have the inner radius, outer radius, and they have a very unique stress and strain constant. But for double wall, it's if for even viscosity even lower to increase the contact area. So we'll have a sample that fill in between the geometries. So typically for less than 1 centipoise sample. So when to use constant cylinder? So typically for low to medium viscosities, not for paste material, because paste materials is impossible for you to fill up the gap nicely without leaving any air within. For unstable dispersion or slurries, okay, this can also minimize the effect of evaporation due to a high sample volume required. And for weakly structured sample, you can use a weight materials, and it can go to even higher shear rates. If you want to achieve like 4,000, 5,000 shear rate, then you can go for a cylinder. Imagine if let's say you want to go for 6,000 shear rate, and you tell me you want to use a cone and plate to same sample, I can tell you it's impossible because your sample is going to splash out in no time. Okay, even though your sample can withstand, can stay on a flat plate, but your sample will be splashes out from the measuring gap. Okay, that's why you need to go for concentric cylinders for this case. And of course, again, I have mentioned on you have a double gap for low viscosity, extremely low viscosity sample, single wall, starch pasting, especially for starch gelling properties. Helical rotor and bowl rotors typically is for suspension. If let's say you have a solid sample, then you may go for a torsion. Okay, this is typically for thermoplastic materials, for a glass transfusion measurements and so forth. And we do have a DMA measurement as well. So beside torsion means they're going to torque the sample in a rotational manner. But we have DMA that do what DMA does. Like you can do a bending, okay, linear displacement. You can do tension, linear displacement, or compressions. So in geometry overview, you have cone and plate, typically for true viscosity measurement or steady state viscosity measurement, typically for viscosity more than 10 millipascal. Okay, but temperature ramp or temperature strip is difficult because you have different thickness, so you may have a lot of thermal lag when you change the temperature, like increasing 5 degrees C per minute. It can be difficult for cone and plate to do that. Okay, for parallel plate, similar, you can have fluids and melt viscosity more than 10 millipascal, but easy handling. Okay, because you can change the temperature, the sample gap to accommodate for your particle size, and you can do temperature ramp. But you are going to have a shear gradient, as I mentioned, so you need to be very careful in trimming, especially dealing with the parallel plate. While for single wall rotor bob, typically for less than 10 millipascal, high shear rate, you can go for a very high shear rate, and it can minimize evaporations. But you need a larger sample volume for this case to fill up the cup. For double wall, again, for sample which is having an extremely low viscosities, but you can go for high shear rate, but the cleaning is quite difficult just because of you need to fill up the slit. Okay, well, for torsion and DMA typically is for solid polymers like film, plastic bar, or fiber. So typically you can only measure at temperature range whereby from glassy to rubbery state. Okay, these two cannot handle liquid materials. Okay, so any questions so far on the theory, the parameters itself, and how this sample parameters is being calculated?
Okay, Mr.
Before I go
Josh,
into, yeah,
Hazris.
yeah.
Okay, I have a question regarding this Rheometer and also this the method that we having used, which is the rotational method. Is it this kind of method can measure the kinematic viscosity also?
What you are having here, kinematic viscosity, you need to have, because what rheometers can go you are going to measure the dynamic viscosity, but you need the
Yeah.
density to actually convert it to kinematic.
Meaning that we can use the result, the value of viscosity, but we need the density, right, for that sample.
Yes.
So
Yes.
if we have that information, the density, so we can convert it into a kinematic.
Yeah, you need to convert it manually by yourself.
Okay, because on the before we start the experiment, at the same time they have information that we need to put it, which is the density. I thought that the value that when we key in, it will affect on the
No, it's for labeling only, that one. It's not
for the
yeah.
labeling.
Yes.
Okay. Second
Your
question.
yeah, okay. Yeah.
Okay, the second question is about the we are facing the problem when we receive the sample. They have a limitation of sample amount, sample volume. Okay, so let's say I have a nanofluid, for example. Our customer is they have a constraint on the sample when they provide to us. So and that because of that, we know that sample is considered as a low viscous. Okay, so due to that, I cannot use the single rotor or single, or another one is double gap geometry. So I have to change to like a cone geometry, cone and plate geometry, because of the sample size. Is it still okay if let's say we change the geometry to the small geometry like a parallel or cone and plate?
For this kind of sample, you can use cone and plate, but please use a larger size one, which is 60 mm or 50 mm that you have. But in loading the sample, you need to be very careful. So how do I load these kind of samples? First of all, I will wet the bottom plate first. Let's say just pump in around, let's say the minimum sample volume is, I would say, maybe 1 ml, just for example. Okay, 1 ml. I will just simply wet it with 0.5 ml first. Wet it first. And then I lower down the upper geometry to measuring gap. Okay, to measuring gap. When it come very close, right, at measuring gap, let's say 0.5 mm. Okay, but it doesn't touch the sample because the sample is very low viscous, but you already wet it, you still have, let's say, maybe 0.5. So when it go to measuring gap, then you use the pipette to use capillary action to pump in the samples via this side. And you can see with the capillary action, it will drag all the liquid and come up from the other side. So when it started to come up from the other side, then you stop pumping in. Without trimming the sample, just go for the measurement. But the limitation of your experiment here, okay, you have successfully loaded the sample, but you cannot go for very high shear rate because it will splash out. So I will generally start from maybe 1 to 100 first, okay, to achieve what I need to achieve. If I get the viscosity already, then it's good. Yeah.
Okay, thank you.
Yeah. So I will just use 1 to 100 first. Even though when it splashes out, when the sample splashes out at 90 or 60, but before the shear rate at low shear, you still can use it. So I believe this kind of sample typically they have they're unfilled and also it's Newtonian, so you just want to achieve a single viscosity point, right? So you can just use the lower shear rate and get the viscosity for your customer. Any other questions? If no question, then I will continue with the flow test, and I'm going to introduce what can a flow test do with the parameters. So when you go for flow test, very direct, your sample parameters that you will get in your result is viscosity. So what's viscosity? So viscosity is typically a lack of slipperiness, and it's also indicate or reflect to internal fractions that happen in your samples. And a more professional terms that you use will be resistant to flow. There are also a unit for them. So typically in Pascal seconds, or poise, or centipoise, or millipascal, but they're interconvertible. So typically you need to also look into these units when you read viscosity results. So again, this is a very general equations of viscosity is actually a ratio of shear stress over gamma dot. So with the gamma dot, you are going to have a shear rate. In some paper, they will write strain rate. So just for your information, strain rate and shear rate are actually equal. They are the same. And these are the typical viscosity values. So you have asphalt binders, 100,000s, all the way down to so sometimes people like to use a log scale for viscosity changes. It's just because it has a huge changes, especially when you have a temperatures program or temperatures sweep in your flow test. So we have a lot of fluid, a kind of fluids in the on Earth. So we have a Newtonian fluids. So this is simplest. Normally, it's just oil, a very clear solutions without any structures. So typically, they are going to have a constant proportionality. So when I say constant proportionality, means the shear stress and shear rate ratio is always constant. So they have only one value of viscosity. Story end. So very simple. But of course, when you started to add particle inside the oil, started to add some structures or modifier or additive inside the oil, it will become non-Newtonian. So because the structure, the oil is being structured, okay, it gets thicker, and the viscosity will change when they are exposed to different shear rate, when they are exposed to different shearing time. So all this will have a very specific name for your sample. Okay, so at constant shear rate, if the viscosity decreases with time, we name this as thixotropic, like a paint sample. When they increase with time, we name this as rheopaxy by considering at the single constant shear rate. Okay, so this is what we call time-dependent non-Newtonian fluids. Right. Well, we have another type of fluids. They are having a different shear rate. They are going to have a different viscosity. So when the viscosity decreases when increases the shear rate, we name this as a shear thinning. On the other hand, when the shear rate increases, when the viscosity also increases, we name this as shear thickening. So these typical results that you get from rheometers, that you have a shear stress and shear rate. So you have the blue one is a very classic Newtonian fluid, while the red one is actually a Newtonian fluid with a yield stress. Meaning to say the sample is structured, but when the structures is break down, they are going to flow Newtonianly. That's why they always start from a y-intercept. So this is how a shear thinning will look like. So when you vary the shear rate, the viscosity will decreases or they are going to increases. So this is some characteristic diagram for shear thickening fluids. So you have dilatant materials that resist deformations. So that's what we call shear thickening. So in flow test, typically you always either displaying shear stress versus shear rate or viscosity versus shear rate, depending on how you want to display your result. But this is what a rotational test will give you in final results. So for non-Newtonian, you can do a time-dependent fluids, okay, where shear rate is constant, but the time for you to shear the samples at constant shear rate would be different. So this will also change the viscosity as well. So for idealized flow curve, typically for sedimentations, leveling, sagging, draining under gravities, you can go for very low shear rate, extremely low, and then slightly increases 4, 5, 6, 7. So you need to have typically in this range. And 8, 9, 10, and 11 typically to mimic spraying, brushing, rubbing, milling, high-speed coating. So you need to go for at least above 1000. So just for a live sample like cough syrup, okay, which material do the better job to coat your throat? I believe if you're sick, then you have a cough syrup. So the cough syrup, of course, you need to have slightly thickened structure, consistency, so that it will stay at your throat longer. Not like a water, you just bring it and that's it. So typically, sample 1 will actually coat or do a better job in treating your coughing symptoms. So for information, sample is being loaded and being sandwiched in between upper geometry and fixed Peltier plate. So typically a flow experiment is like this lady. They're going to stir the samples at a variation of a shear rate or a single shear rate, depending on how you want to set it. So you can do a peak hole or constant shear rate or shear stress, continuous changing of shear stress or shear rate, step flow, flow sweep, steady state flow, or flow temperature ramp. I will explain to you one by one on this. So what is constant shear rate? So this is a single point test. You just want to know the viscosity at this particular shear rate. So you can use this constant shear rate or shear stress, like this hand wash. So just do a shear rate at 1. I only want to know the viscosity of my sample. So you can go for this very simple constant shear stress or shear rate. So this is typically a 2.8 Pascal seconds. While for continuous ramp, so what is continuous ramp? Stress is applied to a material at a constant rate. So this M here, okay, the increased Pascal or shear rate per minute is going to be constant. And the resultant strain is monitored with time. Okay, so this will give you a general yield stress measurements, and you can also give an idea on how my sample behave in a very short time. Okay, this is what we call continuous ramp experiment. Like this, a flow media dispersion. So you can just go for a shear stress, continuous ramp on the shear stress. So we can see this is a Newtonian fluid with structure. So after you break at 10.4 Pascal, they will flow Newtonianly. So for thesotropic lobe, you can also do this continuous ramp up and down. So first of all, you can have the pseudoplasticity or pseudo thesotropic hysteresis lobe for here, ramp up and ramp down. So you get this. Typically, it's for paint sample to capture their thesotropic index by having the areas in between the ramp up or ramp down behavior. Okay, so I believe this is the step and steady state flow that all people will use to get the dynamic viscosities, which is steady state viscosity is what we say. So typically you have a variation of a shear rate, but now you have a time for them to collect the data. So typically they're going to wait the shear stress or shear rate to be constant at the steady state first. Only they will collect the data at every single point. Unlike flow ramp, they're going to just increase the shear stress and get the shear rate, and they are going to collect all the data for you. So typically you have a very period of time, a short time, okay, and then they're going to collect at the end of the first shear rate, and then followed by the second one, and hold for, let's say, 3 seconds. So this soak time here, user need to define how long it will reach steady state. Maybe 10 seconds, 30 seconds, or even 60 seconds. And then subsequently, they're going to have a steady state flow curve. So when you create a step of steady state flow, it will take way longer time as compared to a continuous ramp. Okay, so this steady state flow is very good for example like suspension emulsion or very complicated structured materials. Okay, and this is a series of log stress that allowed to reach a steady state. So each of these steady state is represent to 1 point. Okay, if let's say you set this point to be the soak time to be 6 seconds, so 1 minute 1 point. If let's say you have 60 points, then it will take 60 minutes to complete the whole test.
Mr. Josh,
Yeah.
for steady state, when we set a steady state, and then we know that the default is 1 point to another point is 1 minute, right? 60 seconds. Can we reduce the number,
Yes.
meaning that reduce to 30 seconds?
Yes,
Is there
of
any
course,
effect?
you can reduce from here. The effect would be maybe it haven't reached steady state yet, you already collected the data for you. Yeah. So typically, okay, now you're using DHR, right?
Yes.
Yeah. So I believe in DHR also you have this steady state sensing right here. Okay. Okay, the soak time that I mentioned to you just now is this you mentioned here, right? 30 seconds, 60 seconds. So this is a soak time for the temperatures. Okay. So if let's say 0.1 to 100, okay, you have 5 points. So let's say 0.1 is the first point, the next point maybe is 0.67, you know, they're going to have a 5-point distribute evenly in between 0.1 to 10, 10 to 100. Okay, for every of this single point, if you check this steady state sensing right here,
Okay,
you can always have a maximum equilibration time. Okay, so this is a maximum time for them to collect a single data. Okay, but of course, at certain shear rate, maybe your sample reach equilibrium or steady state before 3 minutes. Okay, they will still collect the data before 3 minutes. How do we actually justify whether my sample have already reached steady state? So remember that you have this curve. So this is a shear stress, and you have a time. So the shear stress have to be reach equilibrium state. So of course you have multiple point here, from point to point, point to point. So the algorithm here is every 30 seconds. Let's say I put here 30. Okay, so every 30 seconds, I'm going to pick a point to build the steady state curve. And this point typically to be considered as steady state, if I take 3 points, I should be within 5% tolerance, meaning that the standard deviation between these points should be 5% lower to be considered as steady state. If this criteria is being met before 3 minutes, I will still collect the data before the 3 minutes end. Okay, if let's say no matter how the instrument collect the points, but still not within 5%, it will collect data at the maximum equilibration time, which is in 3 minutes for this single point. Yeah. If you shorten this time, meaning it wouldn't care like if let's say let's say I shorten it to 2 minutes, but up to this 2-minute period, I still cannot reach this criteria that I set, then I will collect the points for. That's the effect.
Oh, that's okay.
Yeah. Of course, the longer the time means you have higher chance to reach this criteria.
Because some of the customer, they require many number of points. So that one, when we when we set around, if 3 minutes, for example, per points, it's require take longer time, right?
Yeah, but if let's say they are intended for steady state, then they need time. And this is normal for those complicated fluid, because you need to make sure all the particles like flowing in the same directions.
And how about the difference between the flow ramping, or we can say shear ramping?
Okay, this kind of shear ramping that I show you, they're just going to increase the shear stress at the specific rate, and the strain is monitored with time. So they're going to capture every seconds. They don't care whether you steady state or not. This kind of sample typically is for clear solution, unfilled polymer. Or you want to do like paint sample, then it's okay. If let's say your customer mentions steady state flow, you have no choice. You must use this. Okay.
Okay.
So this is some emulsion. Normally flow strips is for those emulsion, suspension, or very complicated system or sample. Okay, with particle inside. So you have this. If let's say you have many points, means the time will be longer because they're going to stay at every single point that you have. But for flow temperature ramp, so typically you hold at a single rate, single shear rate or single shear stress when you ramp up the temperatures, typically to measure viscosity changes versus temperatures. Just like this. So you have temperature changes when you increase the temperatures. So this kind of test normally we'll use a log scale because the changes is very high. Okay. So for rheometers and flow testing, typically you need to we have a control stress and also control rate system. So in the CSR or DHR system, typically you can control either one of them. Okay, either using a shear rate or shear stress.
Mr. Joss.
Yeah.
Let's say if we have the epoxy and hardener, okay, because our customer, they request to determine the changes of the phase, which is at the room. For example, they set the variable temperature, so not a constant temperature, but at high, and then they want to see the phase change, which is from the liquid to that sample become a solid. So we know that the epoxy and hardener, it will become when it become hardened, and then we will start the geometry.
Okay.
So can we proceed with this kind of tests, or they have a limitation, or maybe we have to keep monitor it before it become solid?
Okay, for this is a curing test. First of all, you need to use an oscillation test. Secondly, you need to use a disposable plate.
Or disposable plate.
Yes. Because once you use, you just throw the plate away. Because once it's hardened, you stick at the plate.
Yeah, it will damage sometimes the epoxy or hardener will permanently stick on the geometry, right?
Yes, that's why you need to use advanced pattern plate with the quick change plate for both sides, lower plate and upper plate.
Yeah.
You can do that. It's meant to do that.
Can we use starch geometry?
Sorry, starch?
Geometry.
Geometry typically is a parallel plate for this type of test. So typically you need to have advanced pattern plate with the quick change plate. You have it, right? I think. Do you have it?
Yes, we have it.
Yeah, so for thermoset material like epoxy, hardener, all those things, you must use this kind of plate. After you complete measurement, you just remove the plate and change a new one.
Okay.
Yeah. So when doing a flow test, you also need to be very careful when you have the let's say aqueous solutions. So normally at high shear rate, you have slight increase in the shear rate. It typically can be due to secondary flow, and also sometimes at very low shear rate, you have increase in the viscosity, and this can be due to surface tension on your samples. For sample that will slip like this toothpaste, okay, when I want to measure the yield stress of my samples, so normally yield stress is only a single. It will not have like first drop and then another drop. So this is a sign of wall slippage. Okay, that's where you need to change to a roughened surface geometries to have this single crosshatch plate. Sometimes in flow test, you have this viscosity, okay, and then initially very nice, and all of a sudden it come down like this. So always check your shear stress to check whether this is a sample instability or shear thinning. Okay, from 0.1, so from 10 to around, let's say 1000, the shear stress is still increasing. So from 10 to 1000, this particular range you still can use. But when it started to drop, meaning your sample is leaving the gap, you're measuring only the air, empty sample. Okay, because when you increase the shear rate, the shear stress supposedly need to increase. So this is how we normally check whether this data is still okay or not. So for flow considerations, you have also these possible solutions. If let's say you have edge failure or sample leaves a gap because of normal force, so you can eventually use the Cosmos rules to do, like using a frequency rate and to correlate to your shear rate. Like polymer melt, it's very hard for you to go for high shear rate because it's very thick and you are going to have a brittle break. Okay, I hope you're back. Just for a quick break. Are you there?
Yes, Josh.
Yeah, okay, good. So you're back. So we'll continue with oscillation test, which is a viscoelasticity. So a Rheometers besides can do flow test, you can also do oscillation test. So oscillation test typically is for viscoelasticity. So what is viscoelasticity? So first of all, you need to understand elastic behavior, which is my robot hook, like this three ideal solid, like this three piece of red solid with three loads. So the three is heaviest with the number 2 and number 1. So you have a three typical strain, okay, which is gamma. Right here, so when I plot a graph, stress and strain, so we are going to have a single modulus. So this is ideal solid materials, like a spring. So when we have three type of materials where they have a different modulus.
Mr. Josh, if I can interrupt you with one
Yes.
question.
Yeah.
The principle of Hooke's law, right? Stress is equal to modulus times strain, right? It's almost same with the tensile, right?
You mean flow
Modulus.
or this one?
This one. This principle, modulus is equal as per the formula. it almost applied to you to tensile, right?
Okay, I'll explain to you later on this.
Okay, all right.
Yeah,
Please
yeah.
continue.
But now you just put in mind that what is elastic behavior, because it's important for you to understand viscoelastic. And I'm going to tell you what's the dynamic, what is the differences between tensile and also this one.
Okay, right.
Okay. So of course, general stress over strain, you will still give you a modulus. And of course, if let's say you have higher modulus material, like the black color one, sorry, the red color one, higher modulus, and followed by this green one, and followed by the black color. Okay, so this is what we call strength of materials. Okay, that one is for solid. How about liquid? Liquid, we always use viscous behavior. So solid material, we use what? Modulus. Now liquid material behavior, we always use viscosity. For Newtonian materials, governed by Newton's law, okay, you only have a single viscosity. So same principle, shear stress over shear rate give you a single viscosity. This is only for Newtonian materials here. Now, three viscosity different, same load. So the red color one will have highest viscosity as compared to the purple one and followed by the blue one. Now, viscoelasticity, how? So viscoelasticity means like a polymer materials, like your structured suspension that you add particles inside your oil and it become, sometimes it has it behave like a solid, sometimes it behave like a liquid. So it depending on what do you expose them to. Let's say a fat sample or sample, you put them in a high temperatures, they're going to start to melt. They're going to behave like viscous. So all materials like polymers, suspension, emulsion on Earth, they're actually viscoelastic. Why? They behave sometimes like a liquid, sometimes like a solid, and it also always depending on the load that you apply to them, the simulation, environmental simulation like speed of deformation or temperatures that you give them. Okay. So Hooks and Newton only talk about pure elastic and also pure viscous, but they never mention on the viscoelastic. So which is governed by Kelvin and also Maxwell model now. So now we are going to combine the viscous and elastic model. So now the shear stress is actually governed by the strain rate and also the strain, both two together. You have two models here. One is for creep, one is for stress relaxation, which is Maxwell, consecutive, Kelvin, which is parallel. So the force or the torque depends on both deformation and rate of deformations. Single load and single load. So these models will entirely describe the viscoelastic behavior that used for measurement in Rheometers. Coming back to your question just now, you asked me tensile machine and tensile instrument machines that do flexing, flexures, tensing, or tensile or compressions. Is it similar to what a Rheometer did, right?
Yeah,
they are different.
Mm-hmm.
Because tensile machine, they will not tell you loss modulus, storage modulus. They will only give you a general strength, a general modulus that resistant to change, resistant to the displacement. But in Rheometers, they can tell you the resistance to change is actually based on solid behavior or viscous behavior. Meaning that the resistance to the changes or displacement, it will separate for you. It's actually due to the resistance to flow or the cohesiveness of a solid materials. That tensile machine cannot tell you.
The differentiate
only can you
differentiate between the liquid and also solid.
Yes, it will give you two indexes. One is loss modulus Another one is storage modulus. Storage modulus is G prime. Loss modulus is G double prime. That I will explain to you later. Okay, after this. Tensor machine, it will give you a general strength, tensor modulus, but they do not know the modulus is actually coming from which part. It's the elastic part or the viscous part. But a Rheometer, it can tell you. It's actually the viscous part that resists the movement or the elastic part that resists the movement. Okay?
All right. Thank you, Josh.
So range of materials, behavior. So what you are measuring actually is a viscoelastic materials, which is always in the middle, depending on what temperatures you are measuring, depending on what frequency that you're measuring, or depending on what amplitude that you are measuring. Okay. Well, you need to understand this no matter how. Well, time-dependent viscoelastic behavior. Viscoelastic behavior is very time-dependent, meaning that it always correlate to the speed of deformation. Impact, you give an impact speed, or you just let the impact go slowly. Okay, so when the capital T, the deformation time is very short, your material tend to resist the changes because it's too fast. I want to resist the changes, so it becomes more solid. Meaning that at higher frequencies, your materials will become like a solid. When at low frequency means long deformation time, okay, it behaves like a viscous. So again, the viscoelastic behavior of materials will change not only by the factor of temperatures, but also the deformation time, which translate to your frequency. Okay, this is a capital T. How about this small t? This small t is actually a characteristic relaxation time of a specific materials. Okay, so everything will flow if you wait long enough. Even for a solid, they're going to creep. But of course, you need to wait for a very, very long time, like in years or even decades. Okay, so this de Broglie number is actually the ratio of the characteristic relaxation time of materials. So this is very unique for each and every materials. Just like density, the water density is different, okay, and the oil density is different. So this is another mechanical numbers or value to categorize certain materials, which is your relaxation time. The longer the relaxation time means the more elastic it will be. So it will give you a de Broglie number when you ratio the characteristic relaxation time of materials over the deformation process time. So this small capital you cannot change, okay, because the material is come as received unless you change the molecular structures. But what you can change is actually this one by changing the frequency. So rule of thumb, high de Broglie number solid behavior, low de Broglie number liquid behavior. But you can change this number by changing the relevant deformation process. So we can mimic this in the Rheometers by doing a frequency sweep. So LVR region, this is a very important subject. So the LVR, what do I mean by LVR? LVR means the deformation in the Rheometers is very small, okay, and the molecular arrangement never far from equilibrium. In short, we are actually probing the molecular motion with a Rheometers. Okay, we are probing. We are not like tensor machine, flexural machine, or compression machine, going down all the way, pull the sample until it breaks. But in Rheometers, we don't do that. We are only probing the molecular motion. We are trying to understand the molecular mobility via viscoelastic measurements. Okay, so this linear viscoelastic measurement is very important because it is the domain, the main calculations for all the G prime, G double prime, as well as tangent delta from the results. So what is LVR region and why is this so important? Because we want to make sure that all the frequency sweep, temperature sweep that you do is going to be testing a sample as received. You do not want to test a sample at this region because you have already break the structures. Okay, so we must have all this LVR region by having a sample. When you first receive a sample, the first thing I will do is to do a amplitude sweep so that we can select a good strain measurements in subsequent tests like frequency sweep, temperature ramp, and so forth. So importance of LVR, the molecular structures is going to be a bridge. Okay, when we probe the molecular mobility, we can have the bridge the molecular levels properties on the product performance. So in rheometers, so I'm talking about a rotational rheometers, we are going to always to have a G prime, G double prime. So G stand for shearing. Okay, why we have E? E is for dynamic mechanical analyzer, which is a DMA. So typically E is typically on the tensile mode, tensing mode, compression mode, or the DMA mode, okay, which is only for solid sample. Well, tangent delta is actually your the ratio of G double prime over G prime, and we have the complex viscosity as well, because you can use this test to correlate to your viscosity measurements when you have a polymer map which is very thick and you can go for high shear rate. So what we can do in the oscillation test. So first of all, you need to define the LVR regions, and by using a stress or strain sweep right here, and you can do time sweep, frequency sweep, temperature ramp, and temperature sweep or TTS. Sweep means scanning, so this is just a advanced term for rheometers, where people like to use a sweep instead of scanning. So what is an oscillation? So oscillation is not going, unlike flow test that the other spin in a single directions, but we are going to oscillate the sample in both directions. So when we plot this movement in a graph, in a graphical method in a time scale right here, we're going to have a sinusoidal displacement, okay, which is oscillations. So we're going to apply a dynamic stress to the sample. And of course, this movement here can be low speed and high speed, okay? So we need to govern by the frequency as well. While how far they can go, I mean, how tall they can go here will be governed by the strain percentage or strain. So what is a frequency? So a frequency is time to complete one oscillation. The time to complete one oscillation. So this is considered one. Typically will be governed by radian per second or hertz. You can choose either one to control. So 1 hertz is equal to 6.28 radians per second. Okay, so to be more accurate, you always need to control in the radian seconds. So as you can see, when you increase the angular velocity, so you're going to have more cycles completed in a single seconds. But for amplitude, it's going to have how far the angular displacement going to be. So if higher means further, the sample will be displaced. So typically, you're going to have a deformation, okay, that created by you, and the sample responds to this stress or deformations. And when we deform the sample, okay, the response from the sample not always going to be in phase, okay, with the deformations. But we overlap these two, you can see this is a timeline. The deep blue one is what we are going to apply to the sample, and the light blue is going to be response from a sample. But when you apply the deformation to the sample, okay, not necessarily the sample will immediately or instantaneously give you a response. Maybe there will be a delay. So the delay will be quantified by this phase angle. which is a peak-to-peak delay. The further the delay means the more viscous they are. The closer or the lesser the delay would be, meaning the phase angle will be smaller, then it will be related to more elastic behavior. So for pure Hawking solid, fully solid material like a spring, you place a load to it, it will instantaneously give you a strain. You can see stress and strain is going to be overlapped with no time lag, so they're going to be zero angle, zero phase angle. But for liquid materials, it will take time because it's always going to have a strain rate. By theory, they're going to have a 90 degrees of delay. But for viscoelastic materials, they're going to be always in between 0 to 90 degrees of the measurements. So this is the viscoelastic parameters. So since we are actually applying a complex stress to the sample because it's an oscillation stress, okay? So the complex stress is then going to be separated into two components. So from here, you can see you have a real number and an imaginary number right here. So the real part here is going to be your elastic stress. And the imaginary part here is going to be your viscous stress. So with the elastic stress and viscous stress over a ratio with the strain, you're going to have the elastic modulus or storage modulus or the viscous loss modulus that you can have, which is the energy loss as heat. They can measure overall resistance to deformation. So the tensor machine will give you this only, but Rheometers will give you this separate into storage modulus and also loss modulus. And with the storage and loss modulus ratio up, you can get the tension delta. Okay. Remember, in the Rheometers, we are going to always measure the sample in an LVR region. We are not pulling the sample like tensor machine go all the way to break. We are not doing that. Okay.
Yeah, tensor we go until what we call break.
Yeah, in Rheometer we
ultimate
don't do
tensor
that.
strength. The peak of the tensor will goes until ultimate tensor strength until it broken.
Yeah, so you can see a difference, right? Here it's more like probing molecular mobility.
Elastic.
Yeah, so you can see you have storage modulus and loss modulus. So this is the what we quantify when it hit the ground. So the rubber ball is will be more elastic than the tennis ball, okay, because they have a smaller loss phase. So beside the so the viscosity can also be measured with this oscillation experiment. If flow test is impossible, you can try to going to have this approach. So similarly, they are going to give you a complex viscosity, and the frequency must be in radian seconds, of course, for this state. And the software can help you to transform this frequency strip directly into the typical normal viscosity versus shear rate via Cosmos rules. So for oscillation experiment, you can have multiple approach, which is 5 approach, amplitude sweep. In short, when you can see from the software, time sweep, frequency sweep, temperature ramp, or temperature sweep. So what are they? So typically, the dynamic strain or stress sweep or amplitude sweep is actually a material response to increasing deformations. So it gets further and further at a specific amplitude or at a specific frequencies. And this is a result that you will get. You have amplitude here, and you have a G prime, G double prime, and you're gonna have a LVR region. So these are LVR regions where the modulus is still constant. So when you go for a non-linear region, it will drop. So this is a critical strain. So LVR is depending on temperature as well. So if let's say you have a solid materials, they're going to be shorter, but for liquid materials, they're going to be longer. The LVR, the regions for the LVR. And also it will depending on the frequencies. So the LVRs will decrease with increasing frequencies. So when the frequency increases, you can see it start to drop at lower strain. As compared to lower frequency, it start to drop at only 120%. So it's no point for you to go for high frequencies when you're doing temperature ramp or temperature sweep. But for dynamic time sweep, typically is to monitor the response of the molecular mobility at a constant frequency, amplitude, as well as temperatures. So this is what you need to do. Just now, one questions on the MOSFET, right? So constant temperature, constant frequency, and constant amplitude. The amplitude must be in LVR regions for this case. So importance of time sweep, typically you need to also look into the sample stabilities. So you need to design the test based on the time sweep. So you can use this time sweep as an indicator your sample can withhold how long in the test. Like this, the time sweep on the latex. Because normally when you deal with latex or oil sample, you may use a pipette to load your sample. So you may pre-shirt your sample already before measurements. So always allow your sample to rest before starting the real measurements to avoid this kind of elevations of a G prime. Okay. So like this, sample A, one time sweep, directly measure. You can see like this. When you delay 150 seconds, it gives you a nice LVR. So you always need to have a longer soak time in the conditioning step before starting your measurements directly. So this is a cure of 5 minutes epoxy. So this is the time sweep that you can get the gel point, crossover point, and so forth. So before gelling, you can see G double prime is overtaking. Okay, slightly higher. And after gelling, it becomes solid. So you can see it becomes more solid. So for frequency sweep, it's a material response to increasing frequency. So you can see the amplitude now is going to be constant. And only the speed of deformation is going to be faster. So at a given time, you can see more and more cycles can be fit in, okay, for this frequency sweeps. And this is the material response on the general curve for frequency sweep. So there's a melt region, soften region, EG region, and solid regions. So you can see the G prime, G double prime are going to change. And that's why it's a good method for you to probe the molecular motion, especially for thermoset material, because it involves reactions within the samples. So DHR or HR is actually a CMT, combined motor transducers technologies. That's why they're going to have inertial issues. So this means before moving the samples, they're going to move the motor first. Okay. So both these inertial issues will contribute to your measure sickness. So what's inertia? So inertia typically is a property of metals or materials that manifests itself as a resistance to change. We are measuring resistance to change now. So we want the resistance of change coming all from a sample, not from the instruments. Okay, but instrument has inertia, sample has inertias. So how do we justify every single modulus that we measure is actually coming from a sample alone, not from the instruments? How? Very simple. Call the raw phase angle. So for DHR series or HR series, we are going to correct the raw phase up to 175 degrees C. 175 degrees. How do we validate our measurement data? Simple. You can assess the raw phase angle, and only TA rheometers can allow you to do that. Okay. So when you do a frequency sweep, you can see from here, you can display the phase angle. So remember just now, the elastic stress, the viscous stress. We use this stress based on this phase angle to convert them into storage modulus and loss modulus. So this phase angle is very important. We need to make sure that it's always in the correct phase. So you can see at lower frequencies, the raw phase and the phase angles is eventually overlap to each other. Means the initial effect here is very small and almost no corrections involved. Okay, when you go for higher frequency, means the changes of the machine very high speed. So the initial effect is going to be very high, very pronounced. So you can see it started to go away from the phase angle, and where you need to have the inertial correction come in. Okay, and we can correct up to 175. If above 175, all this point is already invalid, but you still can use the point before it started to shoot above 175. So this is how we actually can validate every single modulus data point by the user itself. So again, you can see the correction for inertia as well from here. Low frequencies, no worries, no problems. Okay, and then it goes up, but not as high. It's still valid. Okay, you still can use it for because we have the inertial corrections right here. What if it's already shoot? What you should do? Change to lighter material plate like titanium or anodized aluminum. Secondly, reduce the frequencies. Well, for dynamic temperature RAM, so you are going to do the oscillation test, but now you're going to increase the temperatures with a specific RAM rate. Okay, so the data will be taken at user-defined time intervals, maybe 1 point per second. It's the fastest data collection that we can go. Well, beside temperature RAM, we have another type of what we call a temperature sweep instead of RAM. So you can see the temperature elevation is going to be like a step. So this is a soak time. User defined. It can be 1 minute, 2 minutes, 3 minutes. Let's say I set 3 minutes. So the first temperature point will hold for 3 minutes at, let's say, 50 degrees C. Only they're going to oscillate at a specific single frequency or multiple frequency. So can do a lot of frequency sweep at the same time. Okay, and this type of test typically will take longer time, way longer than this. And the advantage for this kind of test is no thermal lag because you are staying at that particular single temperature point longer time before you start to perform a frequency sweep. So this is a temperature RAM or sweep material response. So lower temperatures, brittle, solid materials. When it reaches TG, it started to reduce. So transition state, and then a soft rubbery plateau. So the G prime largely reduced at the softened region. And after soften, it go for melt. You can see the loss modulus started to overtake the blue one. So all these changes can be monitored by a Rheometers. So now let's look at the applications. So typically a Rheometers is for not only for Newtonian, of course, it will go for multi-phase system. That's why you need a Rheometers to do it, or else you don't need the Rheometers anymore. Sorry. Okay, so example are paint, coating, personal care product, cosmetic, any system, any type of system that have structured within that you want to see the changes based on, can be based on temperatures, can be based on amplitude, can be based on frequencies or changes. So properties that we will look into will be yield stress, non-Newtonian behavior, thesautropic elasticity. So thesautropic behavior is something like when you break it, it will break, of course, but when you let it rest, it will come back together and form a structure again. So this is a very unique thesautropic behavior like pain. So this is a generalized viscosity curve for suspension. So this is a soft When you see viscosity here, it's always a flow test. Okay, very quick. So first Newtonian, shear thinning, and then second Newtonian, and also possible increase in viscosity due to agglomeration and so on. So just like this, Brownian motion, and then started to achieve steady shear thinning. And then you have thickening. Thickening can be due to turbulent flow, pushed out particles, destroying orders. So you have already destroyed your sample. This is how I told you on the loading the low viscosity fluids if you do not have access to cup materials or you have very small sample volume. So you can just wet the bottom plate and they come down, and you can just pump in the fluid from here. When you see the fluid come out from here, means it's already filled. Okay, so you can stop filling it and you can start running your samples. And also when running this type of samples with structures especially, closing the gap should be always set to exponential so that you do not break the structures by over compressing your samples. I believe yield stress is the most common parameters that people like to find with the rheometers. So typically we have multiple methods to measure yield stress, but the apparent stress is not a single value, but it varies depending on experimental conditions. So why we modify the yield stress behavior? Why people need to modify the yield stress or know the yield stress value? First of all, they want to study a correct yield stress to avoid sedimentation. When you avoid this, it can increase the product shelf life. Okay, they want to also reduce the flow under gravity. During transportation, I do not want my sample sediment at the ground. And they also want to stabilize the fluid against vibrations. When you have a higher yield stress, then the fluid will be more stable against vibrations. So this is how we do a yield stress measurement. So yield stress measurement, we are not going to use a flow strip here. We are always going to use a flow ramp instead. So typically ramp linearly from 0 to a value above yield stress. So typically you can go, you have a value here. So phase motion typically 30 Pascal. So you just have to go all the way up to 90 Pascal. And then you can get the point here. So similarly, you can use also the stress ramp. You can display either viscosity, or you can display shear stress versus shear rate and get this y-intercept. Or you can use certain mathematical to help you for like Bingham. So Bingham is typically to describe a yield stress of a sample that will flow Newtonianly. So you also have a power law. So you have multiple law inside the software to help you. Or flow test doesn't work for you. Let's say for a sunblock lotion, this is a thickened sunblock lotion that do not flow very well in a rotational test. So you can go for oscillation test. You can do an amplitude sweep. So you can do a stress sweep. So this is the LVR region still without breaking. So when it started to drop, you can give yourself a onset point here. Then you can see the critical stress also equivalent to your yield stress. So you can really do a lot of different type of manipulation or tests with the rheometers to suit your sample. You can also use pre-shearing. So for some samples that you need to homogenize every sample, so you can define a pre-shearing before the measurement started to take place. There's a function here, so you can eventually use this to measure the sample. So how do we perform pre-shear? You can use under conditioning step. So you can define the shear rate for pre-shear as well as the duration for the shearing to take place before the measurement take place. This is to remove all the histories shearing due to loading. Okay. So there's a structural fluid 3 ITT tests. So you can have a time sweep oscillation test to check if loading structures destroyed. So if you go up like this, mean destroyed already, but slowly recovery. And you can use a large strain time sweep to actually destroy on purpose for the structures and go back to the LVR strain, okay, so that to check the structural rebuilding properties. Just like hand cream, store should be stable, no sedimentation, because when you open up the bottle, you do not want to see the cream actually separated. And then applications apply to your skin, and it should stay on your skin to form a film. Okay, so it should be able to recover as well. You can also use the mathematics from a software to calculate the characteristic recovery time if you need. So this is how we do it for face lotion A and B. And you can calculate the characteristic reaction time by having a C constant. So this is a deodorant, a storage viscosity applications applied to your skin. And the temperature dependence can also used to govern the behavior during applications to the skin. So you can do this temperature behavior as well. They apply to your own samples. And surfactant properties at the interface. And some personal care product like baby oil, Vaseline, and you can have the so now HR rheometers can also compatible to these tribologist accessories, okay, to calculate the coefficient of frictions. Okay, so so in the software, I believe you already know that you have a lot of getting started guide for you to assess how to monitor data, how to analyze data, how to troubleshoot. So all this inside this tab. And we have a lot of EA tab tips to allow new users to operate the machines without any issues. Okay. And we have e-training course for quick start. Just now you asked whether we have a training course, right? Yes, we have.
Yes,
all
Mr.
this,
Josh. Yes.
Yeah. All this is a quick start, typically for 1 hour.
1 hour? Online? Is it online?
Yes, it's online.
Online, okay.
It's online. You can go for www.tinsurance.com. Okay. Register. Just key in your email and so on, and you can have a quick start, okay, on how to use Rheometers or how to do a rheology data analysis. Quick start.